All right, here's solutions for written problem 8 for Math 252. What we're supposed to do in the first problem is sketch a graph of the region in the first quadrant that's bounded by these two curves. I don't know why I didn't just provide you with this graph. I don't know why I didn't just provide you with those graphs, but I guess I didn't. The graph of y equals x cubed is kind of this S-shaped graph, I guess. I guess that's an S. And then with the 1/8 down in front, it sort of compresses it vertically by a factor of 1/8. So it kind of looks a little bit more like that, maybe. And then the graph of y equals and then the graphic of y equals 2x is just a straight line. Like think y equals mx plus b. The slope is 2. The y-intercept 0. And if we continued these two lines, you'd see they actually bound two different regions. But what I talked about is the region in the first quadrant. So we're looking for this area in here. And what will end up being important are the points of intersection of these two curves. So I'm going to go ahead and label these now, although I guess your picture doesn't really need to label those if you don't want. What I want to know are where these two curves intersect. Well, I could figure out the y-coordinates where they intersect if I just took 1/8 x cubed and set that equal to 2x. Well, to solve this equation, maybe I could subtract 2x from both sides of the equation and then factor out an x. So this tells me that either x equals 0, so that's this point over here, or 1/8 x squared minus 2 equals 0, which is an equation I can solve if I first add 2 to both sides, and then multiply both sides by 8, and then take the square root of both sides of the equation. And when I take the square root of both sides of the equation, really I should put in the plus or minus sign. So really I should get plus or minus 4 here. And you're like, whoa, weird, why are you getting positive and negative answers? Well, because there's a point of intersection up here and another one down here. But since we're only interested in the bounded region that's in the first quadrant, it's just the positive solution to this that we care about. So this right here is equal to 4. And to figure out the y-coordinate where they intersect, if you wanted to do that, you could just take this 4 and plug it into either of these two equations, and regardless of which one you plug it into, you should see that 8 comes out. That's probably more than enough detail for my picture, so maybe I'll call that good. So for 2 and actually 3 as well, what I'm going to do is I'm going to take this bounded region and I'm going to rotate it around the y-axis. And if you rotate it around the y-axis, you kind of get this three-dimensional figure here, which you certainly do not need to draw if you don't want to. That's my best attempt to draw in 3 dimensions. Maybe it helps, maybe it doesn't. The important fact for question 2 here is that since we're going to be using the washer method, we want to think about horizontal slices of this guy. And if you slice this three-dimensional figure horizontally, what you'd be left with is a washer, and the inner radius of that washer would be the distance from the y-axis to this curve, and the outer radius of that washer would be the distance from the y-axis to this curve. And when I'm using washers and I revolve around the y-axis or any other vertical line, my variable of integration is y. So it's not the bounds of x that I'm interested in here, it's the bounds of y that I'm interested in. You can picture infinitely many washers stacked up on top of each other. The first one being at 0, the last one being 8, and infinitely many in between the two. I want to integrate from 0 to 8. And my integrand will be pi r squared minus pi r squared, where the two different r's are just the inner and outer radius respectively. And as this dy kind of indicates, we need our variable in here to be y, meaning we need these curves solved for x. Right now they're solved for y, so I could solve these two curves for x. So for this first one, if I first multiply both sides of the equation by 8, I'll have 8y equals x cubed. And then if I take the cubed root of both sides of the equation, I'll have just x is equal to the cubed root of 8y. And over here, if I solve this, y equals 2x for x, I multiply both sides of the equation by 1/2 and get that x is equal to 1/2 y. You could leave this one in this form, but I think it'll make your life a little bit easier if you recognize that this is the cubed root of 8 times the cubed root of y, and the cubed root of 8 is just 2. So I get that x is equal to 2 times the cubed root of y. You don't have to do that in this step, I just think it'll make the calculus a little bit easier. At any rate, the outer radius is the distance from this axis to the curve, the inner one is the distance from the axis to the line, and the curve is this y equals 1/8 x cubed, which if I solve for x, gives me 2 cubed root of y. So my outer radius here will be 2 cubed root of y, which I'm going to write as y to the 1/3 power. And then my inner radius, which comes from this line, which again is this equation here, is just 1/2 y. And if I could integrate this thing, I'd be done with the problem. And guess what? You can integrate this thing. I mean, I guess you could pull the pi's out in front if you felt like it. And then 2 times y to the 1/3 squared. Well, 2 squared gives me 4, and y to the 1/3 squared gives me y to the 2/3 power. And then 1/2 y squared gives me 1/4, which is 1/2 squared, times y squared. So here's an equivalent integral that's a little bit easier to evaluate. To evaluate this thing, I use the evaluation theorem, which means I need the antiderivative of this guy. The antiderivative of 4y to the 2/3, my new exponent will be 5/3, and I'll have to multiply by 3/5. 3/5 times 4 is 12/5. So the antiderivative of 4y to the 2/3 is 12/5 y to the 5/3 power. And then the antiderivative of negative 1/4 y squared would be negative 1/4 times 1/3, or negative 1/12 y to the third power. And that'll need to be evaluated from 0 to 8. So now I go plugging in 8s and then plugging in 0s and subtracting those two things. Plugging in the 8 will be miserable, but plugging in the 0s will be nice. Let's see if we can do any tricks to evaluate this huge mess of an expression. 8 to the 5/3 power. Well, let's take care of the 3 first. This 3 in the denominator means the cubed root. The cubed root of 8 is just 2. So I get 2 to the 5th power. 2 to the 5th power is equal to 32. So I got 32 times 12/5. Well, 32 times 10 is 320, and 32 times 2 is 64, and 320 plus 64, I think that's 384, although if I messed that up, I wouldn't be shocked. And let's see, what can we do over here? I could think of 8 cubed as 8 times 8 squared, and then that 8 over this 12, 8 twelfths is the same as 2/3. So I take my other two 8s here, 8 squared is 64, and 64 times 2/3 gives me 128 thirds, and then this just evaluates to 0. And you're probably using a calculator at this step, if not before, but I'm going to keep on going. My least common denominator here is 15, so I'll multiply this side by 3 over 3 and this side by 5 over 5. 3 times 384, well, 300 times 3 gives me 900, and 80 times 3 gives me 240, so that 900 and the 200 gives me 1100, and then the 40 plus 4 times 3 is 12. I think that gives me 1152 over 15, and I still have the pi out in front. And then if I do something similar over here, 128 times 5, well, 100 times 5 gives me 500, and 28 times 5 is 140. So 500 and another 140 gives me 640, I think, over 15. And if I subtract the two of those guys, I can get my final answer. Let's see, to get to here from here, I'd need another 512. So I guess 512 over 15 with this pi attached is the volume of the solid that I'm looking for. A little bit worried that I messed up some calculations there without using a calculator. The good news is we have a nice built-in check because we're going to figure out the volume of the exact same region, except instead of using washers, we're going to use cylindrical shells. What you need to know about cylindrical shells is that when we're rotating around the y-axis or any vertical line like we're doing here, our variable of integration is x, not y. So instead of going from 0 to 8, my bound's in the y direction, I'm going to go from 0 to 4, my bound's in the x direction. And since I'm using shells as opposed to washers, I need the formula for the area of a shell. And for that, I'll kind of think 2 times pi times r times h. So there's the 2 times the pi. And then what about the radius of these shells? Well, an arbitrary shell would kind of look like this. So the radius is just whatever the x coordinate is. And then the height of this shell would be the difference in this curve and this curve. So 2x minus 1/8 x cubed. If we can evaluate this, we're done, assuming it equals this. If not, I got to go hunting through this to figure out what I messed up. Let's see, 2 pi is just a constant. That's nice. So I can pull that out in front. I wonder if I can simplify things. I could take the x and distribute it through and get 2x squared minus 1/8 x to the 4th power. And then the evaluation theorem tells me that I need the antiderivative of this guy. See, the antiderivative of 2x squared is 2/3 x cubed. And the antiderivative of 1/8 x to the 4th power is 1/40th, that's 1 over 8 times 1 over 5, x to the 5th power. And that will need to be evaluated from 0 to 4. Much like the previous example, plugging in 4s will be kind of miserable, but plugging in 0s will be wonderful. I change all the x's into 4s and get this expression. Change x's into 0s and just get 0 minus 0, which you don't have to write, but I always do. And now all I got to do is figure out what this mess is equal to. Well, let's see. 4 to the 3rd power. 4 times 4 is 16. Times 4 again is 64. 64 times 2 is 128 over 3. 4 to the 5th power. That's kind of miserable, but I can take one of those 4s and cancel with the 4 that I have down here. So now it's just 4 to the 4th power. That's still pretty hard. Well, 4 to the 3rd power, a minute ago we said was 64. So 4 to the 3rd is 64, and then I still have one 4 left here because one of those 4s canceled with the 4 down here. But that extra 4 that I have, I can cancel out one of the 2's from it with the 2 that's still left down here. What I'm saying is I think I get 128 over 5. And then this, I can actually cheat a little bit here. I mean, I guess I could cheat a lot bit and just say that must be equal to this. But let's make sure that it is. I would have to multiply this side by 5 over 5 and this side by 3 over 3. But I can exploit the fact that I have 128s in both of these spots. So I got 5 128s over here and 3 128s over here in my numerators. So 5 of these things minus 3 of these things would leave me 2 of these things. So up in the numerator, I'll have 2 128s, which is 256. And down in the denominator, I'll have my LCD of 15. And 2 pi times 256 over 15, well, 2 times 256 is 512. Yeah, it looks like this thing worked out. I get 512 over 15 pi. And since that matches this guy, I'm not thinking that I made the same mistakes twice. I'm instead thinking that I got both of them right, and therefore I can end this video.